So Andrew Muir, I am the Director of Strategy and Transformation at Schnieder. I focus on our digital energy space and our power space, so really focusing on building automation, energy management, and microgrids. And my real focus is sort of the mid to long-term strategy of our business, so working with our customers, working with governments, working with what's happening in Canada to ensure that we're able to deliver solutions to meet our customers' needs.
Thanks, Rhonda. Hi, everyone. My name is Chris. I am currently a research postdoc fellow at UBC, and this is an industry-funded position funded by the company Resonance Holdings. So they are, as Holdings suggests, an umbrella company that deals in various types of deep tech, so space, AI, quantum, which is my domain. My research is primarily focused on near-term applications of quantum systems, specifically looking at benchmarking as well as developing metrics to cross-validate the performance of some of these technologies that we see come online.
Awesome. Thanks, Rhonda, and thanks, Anouk, for the invitation to be here, and thanks, everyone, for taking the time to join us for this discussion. My name is Muir. I'm the Vice President of Quantum Technology Evangelism. I know, it's a fun title. It's part business, it's part technical, it's a superposition. It's my job is to help global businesses and organizations to understand quantum computing and the transformational impact it can have for them today. And as Parham was mentioning, I've worked with D-Wave for 22 years, and so in that time I've worked on a lot of different subsystems with quantum computing.
Perfect. So I just want to highlight that DEC did a fabulous job at bringing the experts today, and for everyone who stayed to the end of the conference, you're very, very lucky to have these experts in your hands. So, but to bring together what we had for our for the presentation from Parham back to decentralized energy, I just want to focus in on data centers and the growth of energy consumption related to data in the world that we're in today. So to put it in perspective, the International Energy Association has estimated that in the next 4 years, energy consumption because of data centers is going to grow by 75%. So it's pretty significant. And we already know how much consumption there is today in data centers. We are also aware of the transition with AI moving from maybe a research space, a business space, to actually in the hands of the end users. So for example, I have 2 apps on my phone today. One's ChatGPT and the other one's Perplexity. They both use AI to gather information or use LLM models to change my words. So today, I use both apps regularly, and I'm the end user. It's no longer the business doing the machine learning forecasts. It's exponentially grown. So I'm just going to pass it over to Andrew because I want to get a sense from his perspective with data centers about what this growth looks like on the hardware side and the physical side.
Sure. Thanks, Rhonda. I think ChatGPT is a really interesting example. If you take a traditional Google search for cat versus ChatGPT for the word cat, the amount of energy required for ChatGPT to return that answer is about 10 times as much as it was for Google because of the AI needs. In data centers, and specifically in Canada, I mean, we've got well over 100 data centers operating in Canada. When they first started up, around, if we look at a 5-year period, the amount of power that was required for a rack or a server that they had there, it's grown about 6 times since AI has started to come along. Canada is in a bit of an interesting position when it comes to data centers because of a few things. We don't have the infrastructure and capacity to keep growing at the same rate as we have been since 2020 with the growth of data centers. Land is becoming harder to acquire for data centers to be built and to operate. It's more and more expensive there. So with the rise and accessibility of data centers, cloud computing, the energy requirements that are being asked are becoming exponential. And the other side of things is we've got regulations coming in from the government, right? We've got net zero, we've got scope 1, scope 2 emissions, we've got all these other needs that have to be met within the data center space. So it's a very complex area to operate in, especially from an energy management perspective. So these are some challenges that I think we're all facing. Quantum computing, obviously, as far as we were discussing earlier, is an interesting angle for some of these data centers to potentially look at. But it's certainly a very big risk as we're going forward.
Perfect. So I'm going to throw it over to Murray, because I believe he has an example of how much energy is used in the classical systems versus in the quantum system, and we can hone in on if there's a pairing and a solution in the quantum space for this problem.
Yeah, absolutely. And I really am enjoying this discussion because we're really boiling this down to like the core fundamentals of the challenges we're dealing with in our world. We're talking about energy, we're talking about data, and we're talking about compute. So, when you think about a data center and you think about a computer that's running in it, if you have a single modern GPU, it's going to use almost 3 kilowatts of power. And the power consumption from those GPUs is going up every single year. One of our D-Wave quantum processors uses 15 kilowatts of power, so about 5 times more than a single GPU, but orders of magnitude less than a supercomputer. And the interesting thing is that our first generation quantum computer consumed 15 kilowatts of power as well, compared to our 5th generation quantum computer that we have online right now. The reason that that's the case is because most of the energy consumption is in setting up the environment. We basically have refrigerators that run in our systems, and it's the refrigerator that's using the power, its pumps and its compressors. The actual computer chip itself consumes 1/10 of 1/1,000,000th of a watt. Right. So that's how
That's a lot of numbers for the end of the day.
Yeah, like unbelievably low power consumption, right? And we're talking about data centers going in close to power plants because they're using megawatts of power. So we just did a calculation, as Parham was sort of saying, that the class of calculations that you can do with quantum computers you can't do with classical computers, the regular computers we normally work with. We just performed one in 20 minutes that would take 1,000,000 years with a supercomputer. The power that would have been required to do that calculation would have been equivalent to global energy consumption annually. So there is an opportunity here to offset the kinds of calculations that are very expensive to do with classical computers onto quantum computers. And the interesting thing about those calculations is that they're calculations with quantum neural networks. So, if we're looking at, the really expensive workloads, the ones that are very expensive from an energy perspective, if we can take elements of those and move them onto quantum computers, we can, what is the way that Bonnie Henry described this during the pandemic, bend the curve, We've got this growth in the energy consumption we have for compute. Can we reduce that growth and give ourselves some time as we're developing other sort of green technologies?
So then I'm going to ask the question, what sort of infrastructure do we need in place, or what research needs to be done to sort of bridge this gap to get to the place that we can actually bend the curve? And I'm going to send that to you, Christopher.
Yeah, that's a really nice question, and I think it follows nicely from what we were just talking about with the data centers. So what I really love about quantum computing, and specifically the era that we're in right now, is it's really exciting because the technology is starting to mature, where industry is becoming a lot more amenable or open to exploring this. But also there's still so many interesting questions. And this is not just from the fundamentals of building these new technologies, but also how do we implement them? How do we scale these systems? How do we even evaluate their performance? So many tasks for us to still think about. So in terms of the infrastructure, I think this is really interesting, and it comes down to what do you actually want to do with your quantum computer, or like what is your, I guess, purchase arrangement. So a lot of these are available, the access is available through the cloud, but then you can also have on-premise installations, and this is something that D-Wave they've sold a couple across the world. This is really interesting because, if you've got a dilution fridge and these cryogenic technologies, you need to know how to operate that. So that means a new skill force, new workforce development. The infrastructure can be quite sensitive and tricky to deal with, and all the infrastructure around that. Cooling systems, pneumatic valves, pumps, and things like that. And then what's tricky about that is, what about the future? How do you future-proof this thing? If you're paying like a couple of tens of millions for a quantum computer, what's the longevity of this as the technology grows and, new qubits, numbers of qubits are always scaling up and we're always, trying to get bigger, better systems. So I think there's a lot of open questions around future-proofing these systems. There's a variety of solutions already available. So it comes back down to education and awareness, I would say.
Oh, great. So I've got something on that, but I'm sort of holding off on it for a little bit, on education and take-homes. But I just wanted to circle back on the difference between classical computing and use cases that are appropriate for that versus quantum computing and the use cases that are appropriate for quantum computing in the energy space. So I'm going to just open up the floor to the three of you to if you have some ideas and examples of what are the use cases that are really applicable to our industry, in the electricity industry.
So actually, I use the management of energy grids as a way of teaching people what applications classical computers are suitable for and what applications quantum computers are suitable for. So in a traditional energy grid where you have a centralized plant and then you have basically a hub and spoke model with the transmission lines, then the optimization of the power that you're delivering to your consumers is a continuous one. Do I need to raise the power up? Do I need to lower it back down again? And that power that's going out through the transmission lines to the east is not affecting your optimization for the ones going to the west. In that model of continuous optimization, where the decisions that you're making are independent from one another, classical computers are excellent at that, and we should only be using classical computers for problems that have that type. If instead we're working with an energy grid where we have plants coming online in different places in the network, and sometimes we're going to be drawing power from them, and sometimes we're going to be pushing power. And I was talking with Brent from Iguanatech about like battery systems, and we can think about EVs as batteries, and we can purchase battery systems for storing energy. Well, sometimes we're going to be pushing power into them, and sometimes we're going to be drawing it out. That involves decisions in how you're going to operate your network that are either happening or not happening. You're pushing or you're pulling. And for a classical computer, where each of those decisions affects other decisions in the network, that's a very hard problem for it to solve, and it's exactly what quantum computers are centered on. So the modern energy grid, the decentralized energy grid, the focus of this entire conference is actually a very good fit for the types of applications that we're seeing in quantum computing. And then I want to maybe bring up a couple of other examples because we're using quantum computers in production applications right now. Can I just see by a show of hands, how many people are here from BC and Alberta? Okay, a good representation. So, and how many of you have shopped at a grocery store called Save On Foods? So, great. So Save On Foods has been using our quantum computers for workforce scheduling for more than 2 years now, running in production. If you order groceries at home, the delivery drivers who are bringing those to your home, their schedules are being quantum optimized. And they've now expanded to in-store scheduling. And what makes in-store scheduling complicated is that the workforce is trained to work in some of the departments, but not all of them. They've got time-varying demand by day of the week and week of the year, and they want their workforce to be able to have a full-time schedule, or the schedule, if they're part-time employees, the schedule that they want to have. They're expecting to save 50,000 hours annually with their application, and they're only through the first phase of application deployment for that workforce scheduling application. And in Japan, using a different example, NTT Docomo is using it to optimize their paging signals between their base stations and their cell phone users. And they've been able to reduce the peak usage of the paging signals back and forth by 15%. So that increases the capacity of their base station network by 15% with that optimization. Those are the types of applications that are already running in production. And we're working with folks like Deloitte on airport security scheduling, MasterCard for transaction modeling and fraud detection, and a variety of other customers. So I think, if you think about that video that Louisa put up earlier on about like managing the installation of a fleet of solar panels, well, you've got a workforce which has training to work with different elements of that installation, maintenance, and checking on that equipment. There's a variety of applications in this sector that quantum computing could have an impact for.
So one question I have, Andrew, is understanding this optimization, and it sounds like it's a great pairing of sort of microgrids or smart grids with the quantum optimization model and the computer system that D-Waves has developed. How does that resonate with you in building management?
Yeah, it's a super interesting question. I think we all know that buildings, data centers, every kind of facility we're in is getting more and more connected, more and more complicated. We've got a big change happening in our workforce, right? We've got a lot of experts are starting to retire. We've got new people coming in, and they're coming in to manage these very, very, very complex systems. And quite often, it's a break-fix approach, right? We're very reactive, and we really need to start moving more towards that, predictive type of an application, and being able to understand, with your fleet of equipment that's out there, being able to take all these different variables, all this different information. It sounds like quantum could probably help understand and analyze and optimize sort of your workforce within these facilities to be able to spend their time optimally within their facility to make sure that we're being preventative with our work that we're doing, and also to be able to help us predict when things may be out of line where we need to be sending people to fix them. To me, I was just, when we were talking about this, you think back 20, 30 years, right? There was one TV in the house, you had a remote, there was no phones, there was nothing, right? And now everything is connected that you've got, right? So
All smart.
all smart, right? I've got a friend whose fridge, will text him if he forgets to close it, right? Like it's just getting crazy. So all of this data, it's great. Having data is super, super important. It's super imperative that we have it. But if we can't understand and make sense of this data and why this data is important, it's quite useless, right? So taking complex sets of data to make it simple for people to understand, to have the ability to take action is a critical piece. And I think with the quantum computing, and I have to admit, I'm not an expert, but by the sounds of it, with all of these different variables, all of these different inputs, all of these different conditions, it could be something in the future that could help us with optimization within that space.
So, Chris, do you want to jump in here and sort of connect the
there's
dots?
something that I'd just like to add to that, and this is coming from the quantum computing point of view to what you just said. So I think one of the problems that we've had with quantum computing over the last maybe decade is that it's seen as this esoteric kind of thing, like when will it happen, 20 years, 30 years, like it's unbelievable actually. But if you take a step back and how the technology has actually matured over the last 3 to 4 years, it's definitely become a lot more accessible. You can access these things through the cloud. And a lot of the innovations that we're seeing that's driving the technology is coming from the application space and the end users. So it's no longer a technology that's completely under the control of the physicists. We're seeing this engineers employing these data science people playing with these technologies, developing new algorithms. So it's really important for the technology as a whole to get more interplay or interaction with the end user. And I think that's something that we're starting to see accelerate over the last couple of years. And there's definitely more of an appetite for quantum. And I think it's good for us, and I think it's also good for potential end users that are looking to play around with new types of technologies.
So quantum is very new for myself. I didn't know what a qubit was until about a month ago. And in that process, I also learned about the two different hardware systems to solve quantum problems, which Param informed us and taught us about today. But I just want to bring it back to the use cases. And I understand that it's fundamentally very different to have this gate-based system versus the optimization system. So I'm just going to lean on both Murray and Chris to explain the difference in the form of use cases that we can understand here in the room.
Sure. So I'm always trying to put this into terms that are very relatable, right? So a quantum computer is using quantum mechanical effects to help us process information. So that means that it's a resource for a computer, right? It's, so what kind of resource is it? So in the notion of annealing, when we're doing optimization applications, it's allowing a computer to change state more quickly. So you've got a computer, you've got a grocery delivery driver schedule. The current one is not ideal. You want to move to a better one. You want that change in one solution to the next to be as quick as possible. That turns out to be very important for the types of optimization applications I've been focusing on and talking about in terms of being real time, and available now. In the gate model, the idea is to use quantum effects to allow the computer to store more information. So you're putting a lot of information into the quantum states. It's very powerful. It's also fragile because quantum states are famous for collapsing. And if you put information there and it collapses, then the information you put there is gone. But it's worthwhile for doing these incredibly difficult quantum chemistry calculations. If we want to do a lot of new material discovery in this energy transition over the next several decades, and that's going to be a really important tool if we want to be able to simulate nature at its most accurate level. So that and also fluid flow calculations are the types of things that are going to be targeting that. So when we think about it at D-Wave, we're actually building both models of quantum computer because they have both important applications that they're centered on. The optimization applications that we can run today and into the future, and also the quantum chemistry and fluid flow calculations that we can be doing. And those are just further out. They're more 7 or more years away from being able to have commercial impact. So for you all, it's helpful to know, okay, we can use quantum computers right now. There's a set of applications in the optimization space that we could consider. And if we're thinking about the impact of quantum chemistry and new material design, we might be thinking a little bit further out.
Yeah, something to add to that, which I find really fascinating about the technology as a whole, is the sheer diversity in terms of the hardware that these systems are built on. Because you're dealing with quantum states, quantum is basically the physics of really small stuff at the atomic scale. So there are many types of quantum things. So some of these systems are cryogenic technologies, like solid state actual chips that you develop, similar to CMOS technology. You have to cool it down to really low temperatures. Others are developed by optical systems. So you literally need lasers to drive the light-matter interactions, and you use this to compute. So it's a really fascinating technology because of the sheer range of different platforms that are being developed. But this also makes them pretty tricky to kind of cross-validate and compare results. So in terms of the gate-based systems, there's actually a lot of competing or conflicting information around what is the best benchmarking metric. You'll hear about a whole range of different ones, and that's because all of these metrics, in some regard, will favor one technology over the other. So figuring out these further off technologies, there's still so many open questions, and that's why they're so great to be able to play around with.
So what do you think one hurdle is for the industry to move it forward as a whole and work together? Understanding is it a definition of standards, or I'm just guessing here, but what do you think the industry needs to move quantum ahead quickly?
I want to speak about specifically the gate-based systems. I think probably 3 problems that I think need to be addressed or is getting a lot of attention right now. One, as Murray alluded to, this problem with noise. It's a quantum state, so they're not very stable. They can collapse very frequently. So they have a very high error rate. So making better qubits that are more stable is one thing on the technology side. On the quantum information side, the concept of developing new algorithms and codes to manage the error correction is something that's becoming increasingly popular, and there's actually been a number of really good papers that have come out this year from Google where they've seen a drastic reduction in the resources required for these kind of error correction codes. And the third one, I can't remember what the third one was. So those are the 2 that I would say.
And Marie, on the other side of the system?
Well, I'm going to say, I'm really going to try to put this into terms of in terms of using it right now. I think it has to do with awareness. So my role at D-Wave is to help people know that this technology is available now. I mean, I'm willing to bet that most people here did not know that quantum computers are already being used in production. Everywhere that I go around the world, whether it's Japan, Australia, the Netherlands, Switzerland, all over the United States, when I tell them that quantum computers are being used in production, it's the first time that audience has ever heard about it. So awareness is a big issue, right? And it's about helping people understand that. And that example I gave with Save On Foods, that's actually run by Pattison Food Group. They actually own 13 different grocery brands, so they're going to work on like broadening that out through a broad set of businesses there. But I think the other key thing is that we're not going to do it on our own. We don't have the same kind of expertise that you all have in this sector. And I came here so that I could learn from you how you communicate with one another, to talk to Andrew about what kind of challenges he's facing in his business with energy transition and helping people progress. Because I can tell you that we're moving away from that hub and spoke model, and the other decentralized model, mathematicians have already proven, is like amongst the most difficult problems in the world, which means that we're all about to face this huge complexity growth in the operations of our businesses, and you know that a lot better than I do. So I'm trying to highlight that those are coming and why that's the case and the technology that's there. And Christopher and I are working on solving the complex problems in our fields. And the goal is to remove complexity from your business, not to put that on you, right? I want to work with you on like what's making your business, what's challenging your business, and let's see if we can alleviate that complexity.
That's great. We will have some time for these conversations and questions at the very end here. But before we get there, I just want to understand through our panel and some takeaways that we can pass on to conference goers here at the event that they can bring back to their work, that they can bring back home with them and engage on in the quantum space. So, and for Andrew, I know you're in the same boat as me. We're not experts in quantum, but I will open it up to you first.
Sure.
In the building management and data center side.
Yeah, I think, as I alluded to earlier, right, like as soon as we start talking about these kinds of applications, your brain starts going 100 miles an hour, and I think to your point, Murray, was we don't know what we don't know about quantum computing, but I think everyone has multiple different types of problems that they're trying to solve, and they just don't know how to start solving it, right? So you think about things like energy modeling, right? I'm sure many of you get asked about energy modeling, right? Reducing your greenhouse gas emissions. What's the optimal way to reduce energy consumption, in a facility that you're looking at? Yes, you replace your windows. Yes, you turn down the temperature a little bit, but there's more to it, right? And we think about energy modeling, and it's quite simple. But something like quantum computing, in my mind, can we start adding tons and tons of different variables and looking at all the different outcomes and understanding what truly is an optimal way to run your facility based on a model to optimize, output versus energy consumption. Or, as I mentioned earlier, the whole maintenance schedule piece. Asset management is another huge headache for a lot of people, right? How do we optimally ensure that facilities are always going to be running? So I think from a practical perspective, from my side, right, that's part of it. And then the whole other side of just power and energy distribution, and our grids are getting more saturated with more and more facilities. From a utility perspective, or from even a sub, your own generation facility like a university. Like, how do you ensure you're going to always have the right power available to your tenants, your customers, your clients? So just this brief, discussion with this team started to me questioning a lot of things and thinking this way. And I think that's, to me, sort of opening that door to go like, oh, maybe there is something that quantum can help us with to help solve a real problem that we're having.
Chris, what's one thing from your perspective that everyone could take away and bring back into the office?
Yeah, so definitely wanted to echo what Murray and Andrew were saying about this. It's about the general awareness and the perception around quantum. It's not as far away as what you think. Even these more far-off kind of technologies that are still developing, we're seeing rapid improvements on the technological landscape. And I think in terms of implementation, even if you are experimenting or just exploring this space, this requires a certain set of skills. It's workforce development, it's training, it's education. You need to onboard new systems. So I think there's so much value in exploring this technology, even if you don't need a near-term application right now. and it's right here. Another thing that I want to point out is I think Canada is really well placed in the application space, and I do see a lot of attention from government divisions to make funding available for pilot projects, collaborations, and these kind of things. So I would definitely say that one thing that I would like for people in this session today, speak to your representatives, the consortia. Let them know that quantum is something that's on the radar. The more feedback that federal and your provincial bureaucrats get, the more they understand that there's a need. And we're really lucky in Canada because we have several quantum hardware providers that are actually developing homegrown quantum computers here in Canada. So we should be supporting these initiatives, and we should be working together with them to further develop the field.
How about you, Murray? What's something that you could share for others to take with them?
Well, so I did mention that I came here to learn from you, but one of the things I'll mention is that my first conversation about using quantum computers to optimize decentralized energy grids was in 2012 with Con Edison in New York. So the other thing I would mention is that like this sector is a little bit difficult to enter. You know, the Port of Los Angeles has used our technology to increase the amount of cargo it's handling by 60% every day. So that means the supply chains are more innovative than the energy grid, roughly speaking. And you know, I've participated in incubators in Toronto, and I've met with companies that are pitching and they're creating. And the great thing about being part of an incubator is the company's pitching you, and there's no pretext that you're going to purchase their product right there. You're listening to their pitch, and then you're giving them feedback of like, well, this is what I would need to hear from you to progress, or here's my advice to you so you have a better chance of succeeding with customers. And the question I would have for people in this room is, where is your innovation division in your company? Can you go back in your organization and say, like, do we have an innovation team? Like, could we meet with people who are trying to come up with innovative solutions and give them positive feedback about like what they would need to do to become customers of ours? And you know, I frequently find that the available funding for innovation projects is non-existent or maybe difficult to source, but people are perfectly willing to pay the cost of an inefficient operation at like enormous scales, right? So the cost of running the system inefficiently is so high, but because it's hidden and nobody can be blamed for it, it's sort of like, okay, well, that's there. But innovation involves risk, right? Innovation means I'm going to spend, you know, $500,000 to do a project with somebody. I'm not quite sure what the outcome is going to be. You know, I'm not sure if this is going to work out, and I need to find ways to onboard that journey and de-risk. You know, it starts with discovery. Where are the applications that are relevant? Building proof of concepts, getting that quantifiable return on investment, and then a phased change management plan. And you know, I think it's a conversation starter within your own organizations of like, how do we onboard new technologies? Like, who do we know in our innovation divisions, and can we connect them to some folks who are like the pitches that you've seen here and the technologies? Because we are here to help the sector. I have goals. I would also love to see us transition our energy to cleaner energy as quickly as possible, and so I'm here to help out. And what is the way for us to engage and help you with that?
Great, thank you. So we will open up the questions on the floor. Does anyone have a question for our panel today about quantum? Well, while you think about that, I'll just, do you have a question? Yeah, okay, put your hand up and they'll bring you a mic. But I will say, Param convinced me last night that in a matter of days, maybe a week, I could learn Python myself. I don't know Python. And that I could interact with a quantum computer by just on the cloud and solve a problem. So obviously it's not that complicated to get involved and to learn it and get it started. And to your point, bringing it back and start thinking about the problems that you're trying to solve for your business and in the products you're building and the solutions you're solving. And maybe there's a space for the R&D world to use quantum there. Question?
I just downloaded Perplexity, so I'm going to check that out. But my question is to Murray. I don't know if it's confidential, but I'm so super curious to know what was the problem that your quantum computer solved in 20 minutes that would have taken a regular computer a gazillion years and a year's worth of energy, if you can share it.
Yeah, absolutely. I'm glad you asked that. So we've actually published that work, and we've shown what the problem is, but it's kind of very technical, so it's a little bit difficult to work out. Probably the easiest way to describe it would be like, to put it in the terms of like a neural network, like the ones that are in our brains. So like the fundamental building block of our brains are neurons, and they are either excited or they're quiet. So they kind of like, if you lifted your hand, you're excited, and if you put your hand down, you're quiet. And they have synaptic connections between each other that tend to excite their neighbor or inhibit their neighbor. So if we set up chose a way that we were saying, hey, everyone in this room is connected, and people start putting their hands up, and then you have to look around and be like, well, should my hand be up or down based on how I'm connected? There are ways to connect ourselves up that are very easy to work out. That's the way that machine learning networks are set up, because they have to be made in a way that classical computers can resolve them. And the difficulty with that is it makes the models really weak, and then the data centers end up being really big. If you connect them up more richly, where they can be connected to their neighbors and they can have some frustration in them, then what happens with classical computers is they have a hard time figuring out which neuron should be excited and which one should be off. So the calculation was, what is the dynamical response of a quantum mechanical neural network once it's got a pattern of connections that is known to be difficult? So you basically are looking for how does this brain detect patterns? Which of the neurons are signaling it's detecting a pattern or not? And you can actually watch the patterns change as it settles into what is what the brain is basically thinking. So that's the least technical way to explain that result. But so it's related to quantum materials, like the properties of magnetic materials. It's related to neural networks, which are useful in machine learning. And it also turns out to be a way that it's an algorithm that we use in industrial optimization software. So we can use that to help industrial optimizers move between solutions as it's trying to solve problems.
We had a mic over there, yeah.
There's a lot of people in this room with trying to solve a lot of data processing problems. What would be the steps to do it? It sounds like just coming up with a way to pose the question to one of your computers, and for the foreseeable future, it doesn't seem like this is super portable technology.
Well, that result I just talked about with Chen is on the researchy end of applications. But in the data center impact applications and data processing, we've got some scikit-learn plugins for people who are building machine learning algorithms for recommender systems or for classifying data. So if you're building analytic systems within your business to sort of say hey, is this a pattern that this network is about to fail, or is this a pattern that this is about to go over cost or something like that, or it needs to be maintained, we've got a technique. Usually what happens is that you've got a bunch of very weak features, signal data from sensors that you have in your network, and then you're trying to figure out which of these are predictive that this event is about to happen. You can use our quantum computers to optimize down to a smaller set. And that's actually been used to build machine learning models that you can then deploy through your compute network that are actually more compact and consume less energy. So that's something that if you have a team already working in analytics, they could basically begin working with it and incorporating their workflow in minutes.
That sounds very scalable as a company that builds AI models. We have one more question, our last question for the panel.
Hi, I'm James, recovering astrophysicist, pretty strong background in quantum mechanics, and pretty excited on the one hand by how rapidly things are unfolding and the stories that you guys are able to share, but also a really strong growing sense of concern about the strategic advantage that quantum computing is going to provide to larger corporate entities that can afford to invest in that capacity, and the potential of, basically it's monopolization, that in any particular market we end up with one player who's just got such strategic advantage because they're so optimized that nobody else can effectively compete with them. And I'm wondering if there are any guardrails in place at this point that might prevent that outcome, because I know that the government is not on top of stuff when it comes to regulation of new technologies, things. They're typically way behind the industry. So within the industry itself, as nascent as it is, is there a focus on the ethical context about, using these tools for the benefit of? Because you got one bad actor with their hands on this stuff, it could create a lot of grief in the world.
That's an excellent question.
That's a big one. You got 50 seconds.
I feel like that's such a layered question because there's so many different aspects to this. So nefarious and bad players, generally in the context of quantum computing, we hear about this from state players, so non-friendly, non-allied countries that actually have their own quantum programs, and how we are actually protecting against that. In terms of sovereignty and also security, the cybersecurity threat is obviously a big problem that we need to think about, but corporations are dealing with post-quantum cryptography, and they're really rolling out solutions for that. I think your question is really interesting because you're speaking about it in terms of monopolization of the technology. So I have spoken to a couple of QPU hardware providers, and I guess from the feedback that I hear is it's kind of a mixed bag. There are some players that think that there isn't going to be like a winner-takes-all scenario, and that there's enough diversity in the technology as well as the industry domains that they've already been catering to, that there's enough room for everybody. There are a couple of people that do believe, however, that if there is one significant massive breakthrough, that will be the QPU of choice. I would say that they're definitely in the minority. It's an interesting question because a lot of the big hyperscale companies have their own quantum programs. Google, IBM, Microsoft, AWS, they're all developing their own quantum computers. So I think it's a really interesting question that you pose. Are they going to monopolize?
But fortunately, we're going to beat them all. We do have ethical sessions at our quantum conferences, and we do have groups. There's some folks who are engaged in the philosophy of ethics, and it's a lot about access to technology, access to the knowledge of how to benefit from the technology, and it's in a short-term aspect, it's a very big problem because you just can't get the information out to everybody. And to some extent, the adoption of the technology is based on the idea that you can get an advantage over your competitors with its use. But the long-term direction, ideally, is to end up in a position like an Intel, where your goal is to get everyone access to the technology because then they can use it to build value for other folks. And the economy that's using the technology is much, much bigger than the technology itself. You will end up getting scenarios like NVIDIA, where they come up with a new generation of the system, and for a brief period of time, people will be scrambling to get access to the latest version. And with quantum computing, that actually could even be a bigger delta because with classical computing, it scales exponentially. Like if you double this number of transistors, you're doubling the number of operations. But with quantum computing systems, the scale of the system, the complexity goes up exponentially with the scale. So if you exponentially scale a technology that's exponentially complex, you get like a super exponential growth in the capability. So it's one that I think we'll have to manage carefully and kind of be aware of those issues.
Great. That was a perfect way to end this. Thank you so much. I just want to take this moment to say thank you for everyone for joining us in Whistler. And yeah, it was very nice to have such a expert panel on quantum computing. So thank you.
Thanks.